thank the organizers for giving me the opportunity of visiting this pleasant institution in a very pleasant surrounding. And today I will be talking about pure and mixed entangled states and their Schmidt ranks. So first let me start with a very basic definition which is well known to the specialists in this subject, but I have to give you a brief introduction. For details you may look into the book by Nielsen and Chuang on quantum computation and quantum information. This is about the Schmidt number of a bipartite state. Now, you start with the Hilbert space of a joint system AB, which is a tensor product of two Hilbert spaces, HA and HB, which are associated with systems A and system B, and with dimension dA and dB. And with orthonormal basis IA in HA and JB in HB, they are orthonormal bases. The index I will vary from 1 to dA, and the index J will vary from 1 to dB. Then any joint state can be expressed CAB, which I denote by C, can be expressed in terms of these bases with some scalar coefficients. So the very state gives rise immediately to a matrix Cij, which I denote by C, which is a dA cross dB matrix, where the fact that this is a state, which is a unit vector, that implies that the sum of squares of these coefficients that is equal to 1. Then now you make use of what is called the singular value decomposition of the matrix C. You can express the matrix C as a product, a unitary matrix of order dA and a diagonal matrix where you have positive values lambda 1, lambda 2, extra lambda r, and then rest are zeros, and this is a unitary matrix of order dB. This is of order dA and that is of order dB, and this is a dA cross dB matrix, and this lambda 1, lambda 2, lambda r are nothing but the eigenvalues of A dagger A, root of A dagger A, or the modulus of A. Modulus of A, and it is also the eigenvalues of root of A dagger. Now, the condition that this sigma mod Cij squared equal to 1, that automatically implies that sigma lambda j squared equal to 1. So, to every wave function or a pure state of the joint system, you have a matrix C associated, and from the matrix you have the singular values lambda 1, lambda 2, lambda r, which gives rise to a probability distribution, that is lambda 1 square, lambda 2 square, lambda r square, that gives rise to a probability distribution, and that is also equal to, the sum is also trace C dagger. Now, if you expand this C, namely taking into account that C is a product of these three matrices, you can express C in this form. And so I pull out this lambda k, and if I take uik ia summation over that and denote it by phi ak, and Vkj multiplied by Jb and take their sum and denote it by Ckb. Then you see these U and K, they come from a unitary matrix, and therefore Pka, that is an orthonormal set of vectors, and this is again a unitary matrix, which implies this is another set of orthonormal vectors. These are orthonormal in HA and these are orthonormal in HB. So every unit vector can be expressed in this form where sigma mod lambda k squared is equal to 1. So this is the most fundamental definition, so I will go slow at this moment, because this definition will be used throughout the end. Now if you take from the state C, you consider this rank 1 projection matrix CC, that is the density operator associated with C, and trace out over B. If you trace out over B, you will get a state rho A. So if you perform, that is if you trace out, this will go away, and so what you will get is sigma lambda k squared multiplied by this. And similarly, if you trace out over A, you will get rho B, which is equal to this. So CC is the density operator of the joint state, and rho A, rho B are the marginal states. And important numbers come from here. R, which is the rank of the matrix C which we had, and then lambda k, the numbers which come in this expansion. This is an orthonormal set, and that is an orthonormal set, and the summation is up to R, and this is called the Schmidt decomposition of the state C. This R is called the Schmidt number of the state C. And this R and lambda k are independent of what basis you selected in the beginning. Then the sigma lambda k squared is a probability distribution. The marginal state has got this diagonal decomposition, and so you can compute the Shannon entropy of this probability distribution, which is nothing but the von Neumann entropy of the marginal state rho A. And same thing you can do for rho B, but the von Neumann entropy of rho A and the von Neumann entropy of rho B, they are same. So you have a state, you have a pure state with C, and if you form the density operator and consider the marginal, the two marginals will have the same von Neumann entropy, S rho A equal to S rho B. Now, the important point here is the following. What is the essential difference between classical probability theory and the probability theory which actually arises in quantum theory? Suppose instead of we discuss classical probability theory, the Hilbert spaces HA and HB will be replaced by sets, and the states will be replaced by probability distributions on them. So the joint state will be a probability distribution on the Cartesian product of the sets A and B. And if you take all the probability distributions of the joint system, they constitute a compact convex set. They have extreme points, and the extreme points are point degenerate or Dirac measures, and they are again product measures. And if you compute their entropy, that is 0. So the marginal ones also will again be, the marginal of a degenerate measure is again degenerate, that entropy will also be 0. But here I started with the pure state and then I computed the marginal state, and you have these probability distributions coming here, and there is no reason for the von Neumann entropy S rho A to be equal to 0. In fact, the von Neumann entropy can vary from 0 to the logarithm. You can use the logarithm with respect to base 2 to the logarithm of the minimum of the dimensions of dA and dB. In other words, even though the joint state is pure, the marginal state need not be pure. In other words, the state in the language of quantum information theory, you say the states can be entangled. It was the famous paper Einstein, Podolsky and Rosen in their 1935 paper. This point was actually highlighted, that is, the joint state can be pure, but the marginal state need not be pure. They can have entropy. And that means there will be entanglement. And if you go through the book of Nielsen and Chuang on quantum computation in information theory, the single point which is again and again highlighted is the fact that this existence of entanglement is an information resource. And most of the theorems are demonstrations of this central fact that the states can be entanglement, and the entanglement can be used as an information resource. And the entanglement can be measured by this entropy of the marginal state. The maximum value is the logarithm or the minimum of the dimensions dA and dB, and if this holds, then you say that the state psi is maximally entangled. So for our talk, the basic definition needed is the notion of a pure joint state, Schmidt number R, and the associated Schmidt distribution given by the lambda k square, and the amount of entanglement, namely the entropy of the marginal density operator. The joint state is pure, but the marginal density can have more, can have positive entropy, and the maximum possible entropy is there, and it is attained, and that the state in which it is attained, that is the state of maximum entanglement. This is the most fundamental definition for the subject. So I have written here this. So C is called maximally entangled when R is equal to the minimum of dA and dB, and it is attained when lambda k is equal to this, or the joint state C is 1 over root d multiplied by IA, IB, or you can replace it by any orthonormal basis in HA and any orthonormal basis in HB. In fact, if you apply a unitary in the first Hilbert space and a unitary in the second Hilbert space, that is what you make what is called a local operation, then the Schmidt number, the Schmidt number and the amount of entanglement, they will all remain fixed. They will remain invariant. Right? Now, we had two Hilbert spaces when we took the tensor product. Now let us consider the m-dimensional Hilbert space C to the power m, which is simply Cartesian product of m copies of the complex plane and an n-dimensional Hilbert space C to the power n and take their tensor product. For all computations, it is very useful to identify this Hilbert space with the space of m by n matrices. So this comparison, they are in a way isomorphic Hilbert spaces. Now how do I make the space of matrices into a Hilbert space? You consider the space, then between any two m by n matrices x and y, compute trace x dagger y and define it to be the inner product, and choose and fix an anti-unitary operator j in C to the power n, that is namely the second Hilbert space here. Then define the isomorphism in the following way. Once this anti-unitary operator is given, define gamma j on the product vector uv to be u, then apply the complex conjugation, namely the anti-unitary operator j to v, and consider, that means the product vector in Cm tensor and Cn is taken to this operator or matrix in Cm tensor, this m by n matrix operator. Then a simple algebra shows that is gamma j, there are two scalar products. Cm tensor Cm has its scalar product, and the space of matrices, as I told you, has this intrinsic scalar product. And a simple computation shows that this gamma j is a scalar product preserving correspondence between the total set of product vectors and the total set of rank 1 operators. So if you have correspondence between two total sets, that means two spanning sets, which preserves inner products, then it is a theorem that it can be uniquely extended to a unitary operator. So that gamma j extends to a unique unitary operator between Cm tensor Cm and Mn, namely the space of m cross m matrix. Now you have suppose I choose, here is a proposition, I choose a state C belonging to Cm tensor Cm, that is a joint state. Schmidt number of this equal to R, namely rank of the Schmidt number in the language of wave functions we arrived at earlier. But on the other hand, the gamma j psi is a matrix, and the gamma j psi has got a rank. So the Schmidt number here becomes the rank of that matrix. So the rank of this matrix is a more easily computable number than directly the Schmidt number of the operator C here. So this correspondence is very useful, and the identification of the Schmidt number here with the rank of the gamma j applied to the state is as a quantity is also a very useful computational device. In the joint, you see the Schmidt number itself is a measure of the entanglement, right? Schmidt number is a measure of the entanglement. The entropy of the marginal state is also a measure of the entanglement. So it will be very interesting to find out how rich is the collection of entanglement states. And to this end, and also we would like to construct subspaces in which every joint state has got a Schmidt number exceeding a given number k. So my goal will be construction of a subspace in the joint system HAB, where every state has got a Schmidt number greater than or equal to k. But now because of the proposition, it is equivalent to construction of subspaces in dA cross dB matrices. So you have the linear space of dA cross dB matrices, and here we want to construct a subspace of maximum possible dimension where every non-zero matrix has got rank greater than or equal to k. I consider an example. Write M2n. So instead of M cross n, now I am considering 2n cross 2n matrices. In this case, that you can practically exhibit a very interesting subspace in which every state is entangled and it is of a high dimension. And once I state this problem, it is always said every lecture should always pose a problem to take home. So I would like to conclude this part, the first part of the lecture, with an unsolved problem, which you can take home and try to solve. So we consider 2n by 2n matrices for this purpose. Then in the beginning. Now to construct my concrete example of a subspace where every state is entangled, and which has also the property, this M2n, 2n is also a Hilbert space with the inner product, with the scalar product which I mentioned. I would like every state in the subspace to be entangled, and I would also like every state in the orthogonal complement of that to be entangled. Such a geometric situation does exist in this problem, in this case. So for this purpose, we begin with an interesting concept which is very much used in what is called theory of quantum error correction. You know, if you go through the last few chapters of Nielsen and Chuang, this is discussed in great detail. That is, it comes from what is called the Nel-Laflamme theory. There is something called unitary error basis, and the existence of different kinds of unitary error basis, that itself is a very interesting mathematical problem. And existence of unitary error basis comes from two different sources. It comes from the theory of orthogonal Latin squares in classical statistical designs, and it also comes from the theory of error correcting codes. So let me assume that you have some idea of a unitary error basis. What does it actually mean? You have the space of n cross n matrices, complex matrices. Then it is a fact that it admits, you know that it is a Hilbert space. It admits an orthogonal basis, not orthonormal, but orthogonal basis where every element is unitary. Such a basis exists. And construction of different kinds of such bases and classification of such bases up to unitary equivalence, that in its own right is an interesting mathematical problem. Now I am reminded of the earlier lecture, some connection with the earlier lecture. You say that the tupulins are topological quantum computers. Of course, that is what probably makes mathematicians think about higher dimensions which you cannot visually imagine. So it is not only ordinary quantum computer, it can everywhere vision comes into play, but here you go beyond vision and look at higher dimensions, and there also you need this important concept of imagination and then compute with that higher dimension. That is what we do all the time. So that itself is a sign of consciousness. But what is more puzzling for me is that when you have a complex puzzle and you sort it out, it gives pleasure. And that pleasure, is it also consciousness or is it something else? So this was a question I wanted to ask, but already the earlier lecture was very long. I didn't feel like raising it. So now I have taken that opportunity. Now, so the space of square matrices admits an orthogonal basis of unitary matrices. Now I choose such a basis, namely I denote that basis by W alpha, alpha equal to 1, 2, etc. n square. Oh, I should have here, this is m2n, so the dimension of the space is 2n whole square. So the orthogonal basis also here, it should be 2n whole square. There is an error here. So there exists, choose and fix a unitary orthogonal basis W alpha, alpha varying 1, 2, etc. 2n whole square, or unitary matrix. No, sorry, this is right. Even though this is m2n, I am not doing this, but I am choosing only an n-dimensional Hilbert space, and that has got dimension n square, and I choose an orthogonal basis of unitary matrices of order m, namely elements of the unitary group un, so that the inner scalar product W alpha bar W beta is delta alpha beta multiplied by m. This is an orthogonal basis for the Hilbert space m cross n of dimension n square. So once I do that, the space of n by n matrices themselves, that itself is Hilbert space, and I choose an operator on that Hilbert space. So this becomes a super operator. So the super operator phi, it is an operator from the operator on the Hilbert space of m cross n matrices, and that is, I choose it to be sigma p alpha W alpha W alpha. So this is a spectral decomposition of the operator phi with eigenvalues p alpha, eigenvector W alpha chosen from that basis, unitary error basis. P alphas are strictly positive and all the P alphas are distinct. Then phi is an operator from M1 onto Mn. And you look at the following subspace. Now these are 2n by 2n matrices. I consider the subspace all A, B, but here I put phi applied to B. So this is an n by n matrix. So I consider the subspace of all such matrices where AB vary in Mn. Then clearly S is a subspace of M2n, namely 2n by. So whenever you have M2n, 2n or Mn cross n, I denote it by Mn itself. So with that understanding, M2n is the space of all 2n cross 2n matrices, square matrices. So yes, I carve out a subspace. Now, what was my goal? My goal is to exhibit a subspace in which every joint state is entangled. But by the earlier theorem, the joint Hilbert space can be identified with matrices, the space of matrices. So in the space of matrices, we want to find a subspace where entanglement there means Schmidt rank is strictly greater than 1. So Schmidt rank is greater than or equal to 2. So I want to choose this map. The idea is to have a map phi such that every element in L, every element in these matrices have rank greater than or equal to 2. Right? So my next proposition, I have constructed an explicit example with the help of the unitary error basis, and my proposition is that every non-zero element in the subspace S has Schmidt rank, has rank greater than or equal to 2. That means in the equivalent space of state, in the equivalent joint Hilbert space of order, namely C2n tensor product C2n, if I consider the inverse image of S under the gamma J map, every element will have Schmidt rank greater than or equal to 2. So the aim is the construction of that. So I will prove now every element of this form, when it is not equal to 0, has rank greater than or equal to 2. If either if A is not equal to 0, I have phi B here and B here. B is a non-zero matrix. Phi you saw is the full rank operator. Right? To go back to the definition of phi, all the eigenvalues appear 1 to n square, all the p alphas are positive, so it has got the full rank. So if B is not equal to 0, phi B is also not equal to 0. So you see it has got rank greater than or equal to 2 if A equal to 0, but B not equal to 0. If B equal to 0 and A not equal to 0, then you have A. So again that such an element has got rank greater than or equal to 2. Now consider the case A not equal to 0 and B not equal to 0. So in that case, my claim is the rank of the matrix cannot be equal to 1. The matrix S is this one. The rank of this matrix cannot be equal to 1 when A not equal to 0, B not equal to 0. If it were so, then S will be of the form, if rank were 1, it will be 1 ket vector multiplied by 1 bra vector. So it will have this form. So you will have Z1 eta 1, Z1 eta 2, Z2 eta 1, Z2 eta 2. If it has rank 1, it will have this form. So in other words, A equal to this, but A and A, these two are equal. So Z1 eta 1 equal to Z2 eta 2, and B is Z2 eta 1, and phi B is this element Z1 eta 2. But the first relation implies that Z2 must be constant times Z1, and then eta 2 is C bar inverse eta 1, so that the products are equal. And this is non-zero, and therefore the C is not equal to 0. So which means phi Z1 eta 1 is a constant, non-zero constant, multiplied by Z1 eta 1, which means phi has an eigenvector of rank 1. You see, this means Z1 eta 1 matrix is an eigenmatrix for phi. But this is of rank 1. But you go to the definition of phi. But I have written a rather long argument, but when I was going through yesterday, I found that this is a much shorter argument. Here you have G1 eta 1 is an eigenmatrix, and but in our definition, all the eigen, you go back to the definition of phi, W alpha is a unitary error basis element, and it has full rank, and these are all the and P alphas are distinct. So every eigenvector is a scalar multiple of W alpha, but that is a full rank. But here we of a rank 1 matrix is equal to scalar times the same rank 1 matrix, but rank 1 eigenmatrix is impossible. So there is a contradiction, which means the rank of S cannot be equal to 1. That means every element in the subspace has got rank greater than or equal to 2. But this example has got a curious feature, a curious and very quite a striking feature. Namely, I take now S perpendicular. For the subspace S, I now take S perpendicular. And I examine what is an S perpendicular element look like. It is a 2n by 2n matrix expressed in blocks. So, if you do a simple calculation, it shows that S perpendicular contains elements of the form K minus phi m minus K. It means S perpendicular has a structure very similar to that of S. Only earlier it was A, B, phi B, but here it is A minus A, B minus phi B. That is the only change. And then by the same argument, if you repeat, every element in S perpendicular also has got rank greater than or equal to 2. So, the whole space of matrices, 2n by 2n matrices, is written as a direct sum of two orthogonal subspaces. Every element in the first one has got rank greater than, Schmidt has got rank greater than or equal to 2. Every element in the second one also has got rank greater than or equal to 2. And if you take the corresponding inverse image in the joint Hilbert space of the system, what is the interpretation? If I take two systems with dimension equal to 2n and take their tensor product, which is the joint system, it can be written as a direct sum of two systems, a direct sum of two subspaces, in which every wave function in the first has got Schmidt rank, a Schmidt number greater than or equal to 2. Every element in the orthogonal complement also has got Schmidt rank greater than or equal to 2. That is what this example demonstrates. So now this gives rise to a very beautiful question in elementary algebraic geometry. You see, so I have, as I told you, my dictum, in every lecture one should have a problem to take home. So the problem to take home is the following. What are such decompositions as I have explained here? S direct sum, S perpendicular. What is it? What is the requirement? I want every element in S to have rank greater than or equal to K, or if I go to joint system, every element in S should have Schmidt number greater than or equal to K. Every element in the orthogonal complement should have Schmidt number greater than or equal to L. And then the Hilbert space has got dimension n. The basic Hilbert space has got dimension n. So, problem, what are the triplets, or what are the triplets N, K, L with the following property. Namely, consider the hyperspace of dimension N, C power n. Take tensor product, C power n tensor, C power n. Construct subspaces S, S perpendicular, so that it is a direct sum of the two. Every element in S has Schmidt number greater than or equal to K. Every element in S perpendicular has got Schmidt number greater than or equal to L. Which triplets MKL have this property? In the example which I have given, 2n, 2, 2 is one such admissible triplet. So, of course, this is a problem in the theory of pencils of matrices in the old Italian style algebraic geometry. But with powerful I am not an algebraic geometer, I feel sad for it, but by using those tools, it should be possible to compute all the triplets with this property. In the space of M cross n matrices, consider how to construct a subspace S of maximal dimension in which every element has got Schmidt number greater than or equal to K. And what is the formula for the maximum dimension? That is an interesting, it is a problem which has been solved in matrix solved only very recently by a Canadian group, and it has got many interesting interpretations in the language of theory of entanglement. So I will just go through it just in a few lines and state the theorem only without proof. So consider the variety of matrices of rank less than or equal to K. So by denote by Sk in M and C, namely all M cross n matrices with entries from C, set of all such matrices of rank less than or equal to K. The dimension of the subspace Sk is K times M plus n minus K. It's a very interesting exercise in linear algebra. So the proof is written here in the notes, but we won't have the time to go through. So that is an interesting problem to do. So after knowing the dimension, the next proposition is the following. Let L be a subspace in MMN, let me of course with the entries from C, such that every non-zero element X in L has rank greater than or equal to K. Then you can prove by using what is called the intersection theorem in algebraic geometry, because this L is an algebraic variety. So by using the so-called intersection theorem, you can prove that dimension L is less than or equal to M minus K, N minus K. This again uses only the very classical Italian algebraic geometry, not the powerful Grothendieck theory and so on. Right. So that is the second proposition. Then next one, I have, so the aim is, we have found an upper bound, namely M minus K times M minus K. But then one can construct a subspace. Here I have put the aim to construct a subspace L naught in MMN whose dimension is M minus K into M minus K, in which every non-zero element has got rank greater than or equal to K plus 1. So such a subspace exists, and the construction is somewhat elaborate. And you can explicitly write down ultimately by using this theory in a joint quantum system, HA tensor HB, you can write explicitly a subspace of maximum dimension in which every unit vector, that means every wave function, has got the Schmidt number greater than k, strictly greater than k. You can construct